right, so that was a brief discussion of leading edge devices. Let me just start on trailing edge. So the trailing edge flaps, okay, they're basically a portion of the trailing edge, and they go downwards most of the time. We don't really operate them upwards. But anyway, so they're typically hinged and typically deflect upwards, downwards or upwards if you like. And this will affect the flow around the wing in a certain way, as I will show you. So this picture, for example, here, so this portion here, of course, is the main wing, and towards the trailing edge, you get this flap, and it deflects at an angle, let's say delta here, okay? So this, we call this the trailing edge flap, because it's a flap located towards the trailing edge. So what happens is that these trailing edge flaps, what they do, so remember the leading edge flaps, they extend the stall angle of attack. These guys, they work slightly differently. They actually increase the effective camber of the wing rather than extending the stall angle necessarily. So it's slightly different way of trying to achieve the same thing. Remember, they're all trying to achieve more and more CL to allow you to fly, to reduce the stall angle. So a deflection of the trailing edge flap will increase the effective camber of the wing, which gives you a larger CL. Now, if you guys remember when we had our discussions last year between a symmetric and a cambered airfoil, the first thing I'm sure, hopefully you remember, is that a cambered airfoil for any given angle of attack will always give you more lift. Okay? You guys remember that? So this is the same idea here. So we're trying to increase the effective camber of the main wing, which will hopefully definitely give us more lift. How do you do that? You just put this flap towards the trailing edge, deflect it downwards, it does that. So we have here flow pictures between a wing. So we're not actually changing the angle of attack here of the wing. So the angle of attack in this example is 0 for simplicity. And there is a flap towards the end, and we deflect it by a certain angle delta. So the top picture shows 0 angle of attack of the wing, 0 deflection. The second one is again the same angle. We're not changing the angle of attack, but now the flap is at 15 degrees deflection angle. And just to tell you by kind of in terms of the sign of the angle, if the flap goes downwards, that's a positive deflection. If it goes upwards, it's a negative deflection. The reason for that is to do with the effect of the effect on the lift. If you put the flap downwards, it gives you an increase in lift. So we consider it as a positive flap deflection and vice versa. So what you guys will find is as you deflect the flap downwards, you're going to affect the whole flow field around the wing. So, and actually what happens in terms of the streamline, this is what roughly happens. First of all, the streamlines in front of the wing, they're kind of, they're deflected more upwards. And then towards the final section of the wing, towards the trailing edge, they're really deflected downwards. So this combined effect will actually result in an increased camber, or the effective camber of the wing, which will give you more lift. So that's the idea about having those trailing edge flaps. And as I said, this is just rough sketch of the streamline structures. Here I'm showing you actually the streamlines in terms of their deflections at 5 degree flap deflection and 15 degree flap deflection. Hopefully, do you guys agree with me that there is more deflection of the streamlines at higher deflection angles? Yeah? Can you see that? And that actually tells you, even if I didn't tell you what the angles here, you should be able now to look at flow pictures and say, this is actually must be a smaller deflection angle. This must be a larger deflection angle for the flap, because clearly the streamlines are more deflected in the bottom picture than in the upper picture. Anyway, so the total result is the flap actually increases the effective camber of the wing, i.e. the wing becomes more cambered, like a more cambered section than what it is, which obviously will increase your lift. So let's just see this more clearly here in this graph of the CL versus alpha. So I'm showing you here actually 3 graphs for CL for different deflection, and also for the case where there is no flap deflection, which is in the middle. So the middle flap is no deflection, The one above it obviously is a downward positive deflection. The one below it is a negative one, which is an upward deflection, but we don't really use that. That's not usually how we operate them, but just kind of for illustration purposes. What you guys can see, hopefully, at any given angle of attack along the curve, what you guys can see is if the flap is deflected, let's say in this case by 10 degrees, okay? So this is the trailing edge flap going down by 10 degrees. You guys can see that this thick line, which is just for the main wing with no flaps, is actually shifted upwards, giving you an extra increase in lift coefficient, which we just designed as delta CL. So delta CL is how much the lift coefficient has increased by using the trailing edge flap. So you guys can see. So at a given alpha, let's say here, my lift coefficient, let's say, is here. In using the flap deflection, you guys can see it goes from here to there. So by an amount delta CL. All right, and that's what it does. So along the whole range of alphas, however, if we look very carefully, it turns out that okay, we are extending the lift or improving the lift with using the flaps. However, if you guys look very carefully, the stall angle is actually slightly reduced by using the trailing edge flaps for the wing. So you get higher lift, but the stall angle, as I'm showing hopefully with the dashed lines. So here, let's say is, I don't know, 13 maybe, okay, using the flaps. But for the main wing is actually higher at 15. So the trailing edge flap gave you more lift, but it reduces your ability for extended stall. So the stall angle actually becomes lower. So you have to be very careful how you operate these things, of course. So there is a slight decrease in the stall angle. Is everyone clear? And of course, the lower curve is for a kind of a negative deflection upwards. It does exactly the opposite. To obviously, we don't want to do that. That's not usual operation. But just to illustrate. Okay. Other types of flaps, just to discuss them very quickly. I don't want to bore you this morning, but we can have a plain flap. This is the plain flap. The plain flap, from the name really, is the simplest flap you can have. And of course, it's easy to manufacture, easy to install, blah, blah, blah. This is why usually you'll find it on a number of smaller aircraft, because they want to keep the cost down. They don't want any fancy designs. So it does the job. That's it. So that's the simple design, and it's usually hinged and just goes down. But remember, if you look very carefully, it's the whole section goes down. And the reason I'm saying that is because the next one is called the split flap. Now the split flap, if you guys look very carefully, is only the lower section that goes down, but there is a section that remains. Can you see that? So this section doesn't actually move. So kind of the trailing edge section splits into two. Yeah, one goes down, but the other one remains like this. Whereas the plain flap is the whole thing goes down. Do you guys see that, I hope? So that's called the split flap. Again, it's a simpler design, and it's also used on small aircraft. The slotted one, from the name, so it's a trailing edge flap. It creates a slot. Okay, can you guys guess what the slot will do from our previous discussion? What's the advantage of the slot?
Increase stall angle.
Very good. How is that?
By letting air through so it doesn't separate.
Very good, yeah. So in addition to, of course, so it has two effects there. So first of all, the fact that the flap goes downwards, we are increasing the camber of the main wing. That's one effect. But the fact that you have a slot, now the air will rush through the slot with a high kinetic energy, and then it goes on the upper surface of the flap, energizing the boundary layer of that flap, and therefore it allows it to deflect more with that separation. Because just like a wing, the flap can also separate, right, and can stall. We don't want that. That's not a good thing. So, but the fact that you have a slot now, this allows the flap to go to higher angles, and therefore you also helping the aircraft to go to much higher camber, and therefore much higher lift. Good. The Fowler flap, okay, so they look like this. So they kind of move forward, and then they go downwards. And they're actually they turn out to be one of the most effective ones. They can actually increase the CL max by up to 90%, which is amazing. So what about the other ones? So the slotted one can increase the Lmax by up to 65%. The other ones, the plane, I didn't mention this, the CLmax for a plane can go up by 21%. So you can see it's quite limited, but then it's a simple design and very cheap. Clearly these guys are more expensive to make, but they give you what you want. So this is a decision we have to make. Again, some pictures here. This is a Boeing 737 with its trailing edge flap. It's actually, we'll talk about this in a minute, but this is actually a triple slotted flap. So 1, 2, 3. So you actually get 3 slots. And of course, we know what the use of slots now. The more slots, the better. This is the low surface view of the same airplane, but just from the lower. This is upper view. This is an Airbus A320. You got the trailing edge flaps there showing. And I think this is a picture from before, just showing the leading edge and trailing edge systems. The Fokker 100, that's the has only trailing edge flaps apparently. It doesn't have any leading edge devices, which is interesting. But that's how they decided to design it. And this is a picture, for example, of the split flap on Fragile PT-26. Can someone search for this very quickly? Tell us what type of aircraft? Can't remember. Do you know? Doesn't know? I'm sure it's probably a small plane, general aviation aircraft, I'm sure. It is, yeah, makes sense. All right. Right, we've been talking about lift. Well, it is high lift. Well, our main interest using these systems, of course, is to increase the lift. But we haven't really talked about drag. Now, we all know in life, there is no free lunch, okay? Even if you think you have amazing friends, they are a pain sometimes, aren't they? So, this is kind of the drag. He's a pain, isn't he? Or vice versa. Who's more pain? Him. No, he's saying it's you. It's you. It's good to be honest. All right. So let's just show you some kind of graphs, but I really want you to think really carefully about the effects of drag, because it's quite important. So here I'm showing you really just, sorry, it's not very, very nice curve, but at least you can see the trend. CL versus CD. Anyone reminds me what we call these graphs? They have a name. There is a type of bears that live in the Antarctic. Yeah, that's polar graphs. Okay. I don't know why I have. So anyway, so we're showing you the curve for the drag for different deflection angles from 0. So that means nothing is operated, but you still obviously have the drag curve, to 20 and 40. So what you guys will see typically on aircraft is if we use small deflection angles, you will get a lot of increase in lift with a small increase in drag, which is still okay. We can manage that. The problem is you become more kind of greedy and you want more lift, obviously. And then you keep increasing the deflection angle. The problem is at some point the drag wakes up and says, well, no, you can't just continue like this. And then it starts to increase quite a lot. So there is obviously now, there is kind of an optimum operational range for aircraft in terms of the deflection of the flaps, leading edge or trailing edge, doesn't matter, where kind of you get a lot of increase in lift, but small penalty in drag. However, sometimes we just need so much lift. And it turns out that beyond a certain point, the drag will just go up quite a lot. And so, which actually makes you think about these things, and you have obviously to make a compromise. Now, what I want you to think about probably is increasing drag beyond a certain point by quite a lot. As you guys can see, we get more drag with more deflections, clearly, and actually quite a lot at some point. If we want more lift, that's really a lot of drag, for example, for 40 degrees here. Yeah, if you take the L over D with a lot of drag increase, your L over D will actually suffer. Now, is that a good thing if your L over D suffers in general? Is that a good thing or not? No. You don't want your L over D to suffer at all if possible. The problem is we need to take off and land because we just have to do that, okay? So, what I'm trying to tell you here is while we operate these devices, we're going to have to pay a penalty in terms of reduced L over D. In particular, for example, during takeoff, okay, the reduced L over D, once you take off, you have to climb. So, but if you're climbing, because everything moves so fast, if you're climbing with less L over D, that really makes your climb much harder. Because if you guys look at your climbing performance, which hopefully I think you do in the next term, you will find that it relies on a good L over D. Okay? So it's fine, we've taken off with all these devices, your L over D then is reduced, which then affects your climbing performance. Okay, so honestly, in real life, what people do, they have to think about these two steps, take off and climb. You can't just design them independently, okay? By saying, okay, I just want to take off in whatever lift, I just want that lift, but then you suffer during the climb. And of course, actually, climb itself is a very dangerous situation, isn't it? Because if the aircraft somehow cannot go up, then all sorts of things can happen. So I just want you to think that at a certain point, honestly, the L over D becomes so low that the climbing performance will be affected. Okay, so we need to think about that. Now, just to make life a little bit more interesting, what happens actually, particularly in modern aircraft designs, is actually we use what we call multi-element, whether it's multi-element leading edge devices or multi-element trailing edge devices. And actually we combine, in the end, we use a combination of those two for a particular aircraft. So, for example, the first here, we have a trailing edge flap with a single slot. If you guys can see that, that's a single slotted trailing edge flap. The next design actually has two slots, and then we just call that double slotted trailing edge flap. The third one has 3 slots. Is anyone aware of 4 slots? I haven't seen it. But maybe you know, you're not telling us. No? There isn't. Anyway, so far as I know, you can tell me, but we've only been using 3 slotted flaps like this. In terms of combining with leading edge devices, for example here, no, this is slightly different. This is actually about the configuration for takeoff and landing, sorry. I think that slide is next one. So let's talk about this, why not? Obviously in the cruise, we don't need high lift devices, everything is retracted, clean configuration, okay? Typically in takeoff, we can, okay, anyone with the kind of a hawk eye, tell me what's the difference between B and C?
Very slow, landing.
Fine, but in terms of, just simply in terms of the operation of the devices? Less extending, yeah, very good. So here in takeoff, they're actually what we call partially activated, but landing, they're fully extended. So I'm not saying you're wrong, I just was asking very particular, but this is kind of a takeoff configuration. So partially extended, and the landing is fully extended. So again here, this is just, you can read this in your time. So I'm just showing you here a number of aircraft, Boeing's and Airbus, just to balance things out. And you can check these things. I don't know, I got it from this reference. But they tell you the type of leading edge and trailing edge devices they have. And of course, typically they all have quite a complex combination between leading edge. Even leading edge, they could be double or triple. The trailing edge could be the same as well. Now here, I'm just showing this example because, so high lift build-up. So this is a Clark Y airfoil. You probably have come across it before. And it just shows you, in terms of the various configurations of this airfoil, how the CL max varies. the angle of attack, how it varies with different combinations. And also, remember I was talking about L over D, right? So, for example, let's just actually start from the clean one. So CL max 1.29, usually, to be honest, that's not good for any modern aircraft. You really need much higher than that. So the L over D is 7.5, for example. You stick a trailing edge, simple plain flap, okay? That increases your CL max to 195, very good. But your L over D goes down, right? Because increase in drag, I told you, right? It's kind of the proportional increase in drag is more than the lift you. But obviously here, this is kind of, it must be a situation where they're taking the maximum increase in lift as possible out of it. And I told you, beyond a certain point, if you want more lift, your drag will go up, and therefore your L over D goes down. How about the slotted flap? So the slotted flap is slightly better than the plain flap with similar L over D, so that's good. And then you got all these combinations that you can look at. Let's just, for example, look at, for example, this combination of a leading edge slat with a simple flap. So you get CL max now is 218. Your L over D goes down slightly. This is like maximum operation. The next one, CL max goes up, but with a slotted flap, so you get more CL max. The L over D in this case goes up a little bit. And finally, if you have a combination of a foul, this is a fowler flap, trailing edge, and leading edge slat. Now, yes, your CL max goes up to 3.36, is very good. But your L over D now goes down again. So you guys can see, depending on the configuration, and depending what kind of CL max you're seeking, you have to think about your L over D as well. Because as I said, particularly in takeoff, in climb performance, if you have a very low L over D, that could be problematic. Now, what are some of the issues or problems just thinking about these high lift devices? Well, first of all, really one of the issues is really complexity. They're hugely complex systems because they need a lot of pulleys and a lot of systems to operate, and anything can go wrong. There are obviously also a weight penalty because it's just a lot of things to put together, and the weight obviously builds up. Now, as you know, has anyone done systems engineering? But in general, you might think, if I make something more complicated and it works fine, I'm fine. The problem is, the probability of things going wrong goes up with the number of components you have, right? Because you're connecting things together more, that will actually reduce your reliability if you're not very careful. So you have to think about failure modes. And you do this next year anyway, in year 3. So, but this is something true in aerospace. The more components you have, the higher risk of things going wrong and failing. And if one thing, like a small thing, fails somewhere in the system, that could actually progressively affect the whole aircraft. So clearly, we have to have these devices, but no one likes the fact that we have to care so much about failure modes and weight. The last thing, of course, maybe you haven't thought about, is aerodynamic noise. That's basically, in terms of noise for aircraft, you have two sources. You got the engine noise, and you got what we call the aerodynamic noise or the airframe noise. The noise from these guys is clearly an airframe noise or an aerodynamic noise. The reason for that is you may get flow separation either caused by the flap on the wing or flow separation on the flap itself. Also, those gaps we've been talking about, they're very good for generating kinetic energy and strengthening the boundary layer. The problem with those guys is they actually give you a lot of noise as well. Which, of course, when you guys think about it, we take off and land around airports, and we try over the years to reduce the noise from airports for people living around. So they are a huge noise generator, those systems. So as I told you, it's incredibly complex, as you guys can see. We try to show here as many components as possible, but and of course it's a weight penalty and also noise. So noise, please remember, it's just when you see those gaps and also the flow separation, that what causes the noise. So summary of effects. typical effects, not necessarily always true, but typically. So typically with leading edge, what we do, we try to extend the stall angle, which will give us more lift. However, with the trailing edge flaps, we actually increase the camber, which gives us more lift, although the stall angle compared to the clean one is actually slightly reduced. So these are kind of so this mechanism, the mechanism here is by energizing the boundary layer and making sure it remains constant, not constant, attached over a large number, over a large value of angle of attack. So you're increasing the stall angle here. You're not doing that. You're just increasing the effective camber mainly. Okay.